Now that we've learned synthetic division, we're going to put them to work for us in section 5 in the remainder and factor theorems. The remainder theorem says if p of x is a polynomial where degree is n, and again the fine print, n must be greater than 0, then for any number r, p of x is the same or equal to q of x times x minus r plus p of r, where q of x is a polynomial of degree n minus 1. Let's translate that into words. If you have a polynomial p of x, the function value of p of r, which we did earlier this year by substituting r in everywhere you saw an x, but that's the same as the remainder when we take p of x divided by x minus r. So to find p of r, we can substitute r into the function, as we did earlier this year, into the function p of x everywhere an x occurs and simplify, or we can do synthetic division by x minus r to find the remainder. And that remainder will be the same as p of r, hence we get the name of our theorem, the remainder theorem. So what we're going to do is find p of 2 of the polynomial p of x is 2x to the 4th plus x to the 3rd minus 3x squared plus 5. Now we could substitute 2 in everywhere we see x and simplify. That's what we did earlier this year. I suggest let's use the remainder theorem and put synthetic division to work, since that's such a handy tool. So 2x to the 4th, taking the coefficient 2, then 1x to the 3rd, negative 3x squared. There's no x to the 1st, so I need a placeholder of 0 and a constant of 5. Leave room for a row of numbers, draw a line between my last two coefficients and my dividend, draw a perpendicular line. Everything to the left below here is the quotient. Everything to the right is my remainder. Now here's a very important point, so wake up and smell the coffee. If I'm doing p of 2, it's like I'm dividing by x minus 2. I don't change this number 2. So in the multiplier box, positive 2 if I'm looking for p of positive 2. Alright, then it's synthetic division, bring down the leading coefficients, and from there it's just multiply the number you just brought below the line times 2 in this case, put it in the next column and add, and then repeat that process till we're done. So 1 plus 4 is 5, 5 times 2 is 10, negative 3 plus 10 is 7, 7 times 2 is 14. When we add 0 plus 14, we get 14. 2 times 14 is 28, and 5 times plus 28 is 33. In this case, since we're just doing the remainder theorem, ignore the quotient, and we're just looking at the remainder. We know that p of 2 is equal to 33. And because synthetic division goes so quickly, and I tried to do that one quickly since we learned it in the previous lesson, to illustrate that that's probably even faster than substituting 2 everywhere we see an x and simplifying. So the remainder theorem says when you have a polynomial p of x, you're looking for p of some number value. Instead of substituting in everywhere x occurs that number, we do synthetic division by that number, not its opposite, and the remainder is my value of that polynomial evaluated at 2 in this case. Now we have another theorem, which is called the factor theorem, as opposed to the remainder theorem. It says if you have a polynomial p of x, how do you know if x minus r is a factor? Well, it's a factor if and only if this is true. R is a root of the equation p of x equals 0. Let's translate that into words, and what that means is, just like we learned in the previous lesson, if your dividend divides evenly by your divisor, meaning your remainder is 0, then they divide evenly, and of course it's a factor if you have two numbers that divide evenly. So let's say p of x is x to the 12th minus 3x to the 8th minus 4x minus 2, and we want to find out if x plus 1 is a factor. So let's set up synthetic division. We have a lot of placeholders here. 1x to the 12th. 0x to the 11th, 0x to the 10th, 0x to the 9th, negative 3x to the 8th, 0 for x to the 7th, 0 for x to the 6th, 0x to the 5th, 0x to the 4th, 0x to the 3rd, 0x squared, minus 4x, and negative 2. Now we're not asking to find p of some number, we're asking to divide. And when we divide, that's when we take the opposite. So if my divisor is x plus 1, I want to use negative 1 here for synthetic division. Bring down the leading coefficient. There's a lot to do here, so let's just multiply, put it in the next column and add. Draw it below the line for the sum. Multiply, put it in the next column and add, etc., etc. So 1 times negative 1 is negative 1, which plus 0 is negative 1. Times negative 1 is positive 1, which when we add it to 0 is 1. Times negative 1 is negative 1, which when we add it to 0 is negative 1. That negative 1 times negative 1 is 1. Put that in the next column and add it to negative 3 to get negative 2. Negative 2 times negative 1 is positive 2, which added to 0 is 2. 2 times negative 1 is negative 2, which added to 0 is negative 2. Times negative 1 is positive 2, which added to 0 is 2. Times negative 1 is negative 2, which added to 0, of course, is negative 2. That negative 2 times negative 1 is positive 2, which added to 0 is 2. Times negative 1 is negative 2, which added to 0 is negative 2. Times the negative 1 is 2, which added to negative 4 is negative 2. Times negative 1 is positive 2, which now finally we add that to negative 2, we get a remainder of 0. That's the importance here. Forget about the quotient for this problem. It just says determine if it's a factor. Since it divides evenly, yes, x plus 1 is a factor of my polynomial x to the 12th minus 3x to the 8th minus 4x minus 2. Now, aren't you glad we're doing this using synthetic division rather than long division? So, yep, factor theorem, if you divide and you get a remainder of 0, then your divisor is a factor of your dividend. That's putting it into words. All right, we're going to go backwards a little bit here, something a little different. We know the answers. We want to find the equation. Now, the fundamental theorem of algebra, which, again, the book hasn't got to yet, if we had x to the second, we're looking for 2 answers. And here, since I've got 3 answers, my polynomial is probably an x to the third, or what we call a cubic polynomial. But I know that x equals 1, x equals negative 2, and x equals 3/2. We're going to use the zero product property backwards. And if those are my solutions, let's get the 1 over with the x by subtracting. That gives me x minus 1, which is a factor. Bring the 2 over with the negative 2 over with the x by adding it. X plus 2 is a factor. And if x is 3/2, then x minus 3/2 is a factor. Those are my 3 factors, which if you briefly look at the zero product property forwards, set each of those equal to 0, you get each of your answers. So we're using that zero product property backwards. But let me multiply both sides of the equation by 2 because I want to avoid this fraction here. So my factors are x minus 1, x plus 2, and 2x minus 3. And those are my 3 factors that equal to 0. Well, the strategy from here, if I can multiply all 3 of those binomials together, I will get my polynomial. And yes, if we have an x to the first times an x to the first times an x to the first, we should get an x to the third. Now, when multiplying 3 numbers, nobody can do all 3 at once, so pick 2 of them to multiply first. I suggest the first 2 here, and let's FOIL it out. X times x is x squared. Outside is positive 2x. Inside is negative 1x. Last is negative 2. Let's simplify that because 2x minus x is positive 1x. And now we're back to chapter 4, where we learned in the beginning of the chapter how to multiply a trinomial times a binomial, which we described as essentially double the distributive property. 2x has to get multiplied by each term in my trinomial, and then negative 3 has to get multiplied by each term in my trinomial. So let's do that. 2x times x squared is 2x cubed. 2x times x is 2x squared. 2x times negative 2 is negative 4x. Negative 3 times x squared is negative 3x squared. Negative 3 times x is negative 3x. Negative 3 times negative 2 is positive 6. And I line them up with like terms, so when we add 2x to the third, negative x squared, negative 7x plus 6 equals 0. that's my polynomial. So the polynomial p of x is 2x to the third plus x squared, minus x squared, minus 7x plus 6. All right, well, let's continue in the process. Eventually, we need to solve any and every equation, especially cubics. So if I have x to the third plus x plus 10 equals 0, the fundamental theorem of algebra tells me I should have 3 answers. Example 3, we did this backwards, went from the 3 answers to the polynomial. At this point in the chapter, we're going to go from the polynomial and try to find all 3 answers. Only to start us out nice and easy, this example is going to give us the first of those 3 answers. Negative 2 is a root. What should we do with that? Well, synthetic division. Have a coefficient of 1x to the third. Need a placeholder of 0 for x squared. Coefficient of 1x, constant of 10. If negative 2 is a root, zero product property backwards, x plus 2 is my factor. But if negative 2 is a root, I'm going to do synthetic division with negative 2. And we're going to end up with, if it's a root and they're telling us that, I better end up with a remainder of 0. What we'll do then is look at that quotient to see if we can find the other 2 answers. So let's start with synthetic division by bringing down the leading coefficient. Multiply by the negative 2, put that in the next column and add, which of course added to 0 is negative 2, times the negative 2 is positive 4, put that in the next column and add to get 5. 5 times negative 2 is a negative 10. It better be, because 10 and negative 10 give me a remainder of 0. And if they're telling me it's a root, then it should divide evenly. So let's take a look at that quotient. We can ignore the remainder since it divides evenly. That's 5. That's my coefficient of x, my coefficient of x squared. So I have x squared minus 2x plus 5. Sounds kind of funny. We call it a depressed equation. No, it doesn't need to see a psychologist and work out its troubles. It's a depressed equation because it started out as x cubed. Now it's down to x squared. Maybe that's why it's depressed, lost some of its powers. But we know now how to solve quadratic equations. We learned factoring, completing the square, quadratic formula. So let's solve x squared minus 2x plus 5 to find my other 2 answers of the 3 that we're looking for. If we use the quadratic formula, a is 1, b is negative 2, c is 5. And we've done the quadratic formula so many times now, let's just substitute the numbers in. Simplify, so that's 4 minus 20 over square root of that, and all of that is over 2. 4 minus 20 is negative 16. Yes, remember previous chapter on imaginary numbers. Square root of negative 1 is I. Square root of 16 is 4. Now I've got a greatest common factor in the numerator of 2. So when I factor that out, 2 divided by 2 is 1. 4i divided by 2 is 2i. And the 2 in the numerator, that's a factor, with the 2 in the denominator, that's a factor, divides out. And that leaves me the other 2 answers, 1 plus 2i and 1 minus 2i. So a quick review, we started out looking for 3 answers, but we were given a heads up by being told the first answer. Did synthetic division, got a depressed equation, which was a quadratic, put it in the quadratic formula to find the other 2 answers, and they were the complex conjugates, 1 plus 2i and 1 minus 2i, which is another theorem we'll get to, is when you get a complex root, you should also have its conjugate. So that's our look at today's lesson, and picking up the remainder theorems, the factor theorems, and starting to solve polynomials to find all their roots.